Hey guys, Buildzoid here from Actually Hardcore Overclocking, and today we're going to be taking a look at the Radeon VII reference PCB from AMD. It's very interesting. It's one of the first times I've seen a PCB and gone like, I mean, there's a few other cases where this has happened, but this is like one of the more recent ones where I've gone like, I have no idea where anything is, because of how complicated this thing is. Well, how many different voltage rails are on this thing? Well, different regulators and rails. You know, you need different regulators for your different rails. So,
before that, this video is brought to you by Thermaltake's Core P3 case. The Core P3 is one of the most unique cases on the market. It can serve as an open-air standing chassis, a test bench in vertical or horizontal orientation, or as a wall-mounted showcase PC. The Core P3 now comes with a 5mm thick tempered glass panel for its side, but keeps the front, top, and back open for air. The Core P3's versatility as a display piece, test bench, or standard desktop is reinforced by its price of roughly $110 on Amazon. You can learn more at the link in the description below.
Anyway, let's get right into it. And so starting off with the largest and most important VRM on the card, the V-Core, which in typical AMD, not really. So, you know, in the past with like the Vega 64, AMD AMD had like the most powerful consumer consumer GPU VRM, right? It was like on par with extreme overclocking cards. This VRM could have been that. Like, in fact, this VRM could have been more powerful than what you get on a 2080 Ti, but you know, that basically means it isn't. So this is the lovely V-Core on this, and it is still very, very powerful and still very, very efficient. It's just not as ridiculous. Like, I'm sad that it's not as ridiculous as it could have been. Okay, I'll be honest with you. I really wish that this was still fully populated. And also we can kind of see up here, you know, in the PCB, normally there'd be a little switch thing with a nub that sticks out in that little slot that they have cut. So yeah, that is where the BIOS switch would have been if AMD had bothered to include it. But anyway, back to the VRM, which the reasoning why these phases are missing is actually really, really simple. In typical AMD fashion, AMD has opted for some very nice and very expensive power component. They're not MOSFETs, they're power stages. There's MOSFETs in them, but, you know, it's significant enough difference that I wouldn't call these MOSFETs. So they've opted for some very, very nice power stages, which historically they've really just gone for like really nice MOSFETs. And then, well, actually, no, they did use a lot of, well, yeah, power stages as well. So anyway, AMD likes their high-end, high-end power components. So they've gone for TDA, International Rectifier, or Infineon at this point, TDA 21472s. These are 70 amp smart power stages. So at this point you might be like, oh, so it's like the same thing as the FDMF 3170s that you find on like NVIDIA reference cards. Actually, most of the RTX 20 series. Well, no. These are about twice as expensive as an FDMF 3170. These are about $4 a piece, and that's even if you're buying 50,000 of them. So basically, by not including these these four phases right here, AMD is probably saving around $20 on the V-Core VRM, which makes sense because I mean, this card is supposed to hit a price point of $750 retail, and that right there is really, really expensive too. So, you know, it's just like, well, you got to start saving costs somewhere, right? And this isn't going to get cheaper. That has a relatively fixed manufacturing cost, and I'm not even sure if it's possible to manufacture HBM GPUs without all of the HBM populated. Because if you look at like the Titan V, right? The Titan V only has 3 active HBM stacks, but there's 4 of them on the chip. So yeah, that's one of the reasons why I'm wondering if AMD even has a choice about, you know, going for less HBM with this thing, because it's just like, well, it might cost more to assemble than it costs to buy the actual stacks. And so the issue is that you can only assemble it as a 4-stack configuration, not as a 3 or a 2. Anyway, and a 2 would probably have bandwidth issues, but anyway. So, you know, trying to save some money on the VRM, and then getting the really, really high-end power stages. Now, what makes these kind of special compared to, say, the FDMF 3170 is that because these are, you know, 70 amp smart power stages, so that means they have all of the usual features like over current protection, over temperature protection, built-in current monitoring, built-in temperature monitoring, you know, all kinds of cool features like that. Which makes them a smart power stage, but because these are also made by International Rectifier and extremely expensive, they also come with features like they can run at switching frequencies as high as 1.5 megahertz, whereas the FDMF 3170s, which NVIDIA likes to use, those go only up to 1 megahertz. Not that that's a particularly useful difference, because most of the time you will never run your voltage regulator at that kind of frequency. It ruins your efficiency. But these also include something called body braking mode, which is a standard feature for International Rectifier power stages, which essentially is used for load transients on load release, which basically minimizes your voltage overshoot on load release, which is a really, really cool feature. But yeah, so that's something the FDMF 3170s just straight up don't have. So essentially what that allows the body braking, what that does with these power stages is essentially, if you go from a high current draw to a low current draw condition, you can stop using the low side MOSFET on these, and that forces all of the current to flow through the body diode, and the body diode has a bunch of voltage drop, so you can very quickly burn off the energy stored in your inductor without getting as high of a voltage spike as you normally get when you go from a high current draw scenario to a low current draw scenario. So that's a pretty cool feature that these have, and that also adds to their cost. And they're also ever so slightly more efficient than the FDMF 3170s. For comparison, because both are spec'd for like Intel CPUs at 1.8 volts, the TDA 1.8 volts output, the TDA 21472, pushing 40 amps only dissipates about 5 watts with 600 kilohertz switching frequency, whereas the FDMF 3170 would dissipate about 5.6 watts with 500 kilohertz switching frequency. And then if you go all the way up to 60 amps output on these, on a single one of these would produce only about 10 watts of heat, whereas the FDMF 3170s produce about 12 watts of heat. So these are slightly more efficient. They have slightly higher switching frequency capabilities, and they have body braking mode, and that's why they're twice the price. So yeah, that's kind of, you know, AMD for you. They really like their high-end power components. Unfortunately, they can't actually have that many of them on this card. I'm kind of, like, they should do like a special extreme overclocking edition of this card with a BIOS switch and voltage controls and no power limit and no boost algorithm. That would be great. And fully populate the VRM and charge $1,000, and I'll buy it. I'd actually probably buy that. Anyway, so yeah, that's our power stage here. The phase count for the VCore VRM is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 phases, and this is an actual 10-phase configuration. It's not a true 10-phase, because AMD is still going with their ever so popular, well, with their favorite voltage regulator, which I'm pretty sure is built just for them, the IR35217, which we've already seen on like Vega 64 and Vega Frontier Edition. This thing goes up to 8 phases. There's no data sheet on for this thing at all, but one would assume that this being a 352-200 series chip, it'll go up to 2 megahertz switching frequency if you so desire. You know, you wouldn't actually do that because it'll ruin your VRM efficiency, but you can. And yeah, it goes up to 8 phases. And here it's actually running in a 5+1 phase configuration. If the VRM was fully populated, it would have been running in a 7+1. But as it is, it's only configured for a 5+1. And then it is doubled into the 10 phase by these chips right around here. So, and those are, of course, because this is an International Rectifier VRM design, these are, of course, IR3599s, which are, like, their main feature is that they can go quadrupler. They can run as a quadrupler, so you can go from, like, 5 phases to 20 with these. But here they are only used in doubling mode, and the downside to them being quadruplers is that they do the most basic of doubling possible, where they essentially take the PWM signal and just put it, split it between the 2 phases. which basically means there's no current balancing. And as far as the voltage controller is concerned, this is a 5-phase. But the 3599 does have the advantage that like you still get the reduced output ripple because your phases are all interleaving, right? So you do have 10 different PWM signals on the actual power stages themselves. So you get the reduced output ripple, you get the reduced input ripple, but you just don't get any, like, since you lack current balancing, your VRM efficiency isn't quite as high as it could be if it was perfectly current balanced and all of that kind of thing. But you know, that because as it is, the IR35217 is doing all of the current balancing, and it does it in groups of 2. So it'll like take this block right here, which is 2 phases, and it'll current balance that against this, and against this. It will not actually current balance the 2 phases in each of the, like the individual phases within those blocks will not be current balanced at all. But yeah, still, like, as far as VRMs go, this is definitely not a bad design. It's just like, it's the limitations of going with international rectifier, and the only company doing like fully current balanced voltage, current balanced doublers are Intersil, and they're really expensive to run. So they're like even more expensive than international rectifier parts, because you'd be like Intersil. I'm not sure Intersil even makes a 70 amp smart power. Well, they do make a 60, but I'm not sure they make a 70 amp smart power stage yet. And the doublers that they like, the current balanced doublers from Intersil, I think are like $1.5 a piece in bulk, at least last time I checked them. So, you know, yeah, not really a great option in terms of keeping low, you know, keeping your costs low. Not that international rectifier is much better, but it's not quite as bad, because at least the doublers are like $0.50 each instead of $1.50. Anyway, so that's our VCore VRM. Another interesting thing to note is that we almost have a full U. You know, AMD was the first to come out with the L-shaped VRM. NVIDIA kind of, in my opinion, one-upped them with the double I configuration, where you have one row of phases on one side of the of the core, and then the other row of phases on the other side of the core. And essentially what that means is when you are pushing power to the GPU core, what happens with a standard sort of VRM layout where you just have one row of phases on one side of the core, as you push current into the core, you get a voltage drop across the power plane. And so essentially this side of the core has less core voltage than this side. And you can actually check that on GPUs while they're running. If you measure the bypass capacitors on the back of the GPU core for vCore, the ones furthest away from the VRM will tend to have a couple millivolts less voltage than the ones nearer. Sometimes as much as like tens of millivolts. So yeah, and on like a Vega with the L-shaped VRM, you could actually measure, like in this corner, you'd be measuring like 1.2 volts. And if you measured in this corner, you'd measure 1.17, right? So you'd have a difference like that. So this VRM, I mean, it's not a full U. If they went for the full U, then you'd have like this point right here. That would be your lowest voltage. But with this configuration, that point will very likely be, actually, we should go like that. That point will very likely be right here again. But it'll be interesting to see how much of a difference it would be from like here, right? Like across there, what kind of voltage difference you'd have. It should be very low, because this is getting very close to almost like a full surround. I wonder if we'll ever see an O. But anyway, so that's kind of interesting that AMD has the VRM laid out like that. And that does mean that you get a bit more uniform voltage on the GPU core, which in theory means you'd have a bit better clock margin for any given voltage, because ultimately your lowest voltage is also going to affect, like your lowest voltage going into the core is going to obviously limit your maximum frequency. So anyway, and it does mean you also have a bit better efficiency because there's less voltage drop across the power plane, but that's really a minor thing. Anyway, so that's the vCore VRM sort of, you know, not taking a look at the power efficiency. So let's take a look at the power efficiency. The TDA 21472s make this VRM ridiculously power efficient. And for my convenience, they're also spec'd at 1.2 volts. So 1.2 volts output, 400 kilohertz switching frequency, and a drive voltage of 5 volts, which is standard, which also means we have a 5 volts regulator somewhere on the card. I'm not sure where. Because we have like regulators up there, up here, this thing, that thing, and we'll get to those eventually, but those, like, then we have another regulator down here. These are like the minor ones. There's also like, I assume this is a regulator, but that might be 5 volts. Fortunately, like, there's rails everywhere on this card, and I'm not sure which one specifically is 5 volts. But there is a 5 volts rail somewhere on the rail, somewhere on the card, because these run off of 5 volts, being a smart power stage that's pretty standard for them. Now then, they are spec'd at 1.2 volts, 400 kilohertz for my convenience. The card does not run on 1.2 volts, right? It's 7 nanometer. It runs on a lot less voltage than that. But anyway, so 200 amps output at 1.2 volts, you're going to be looking at about 15 watts of heat dissipation on this VRM, which is crazy efficient. Like, that is really, really, really great efficiency right there. It's just about 94% efficiency. Actually, it's not exactly 15, okay? Because if you actually go, if you go with that 15 watts figure at 1.2 volts, 200 amps, you're going to get like 94.1% efficiency. Yeah, that doesn't work out. It's like 15.5 or something, because it's just barely under 94% efficient. This VRM is at 1.2 volts output, 200 amps. So yeah, but about 15 watts. So, like, you shouldn't need a heatsink on this. You really shouldn't, if you're only pushing 200 amps. Now, going up to 300 amps output, this VRM is going to still only produce about 20 watts of heat, which is, again, like, there's a crazy efficiency. Like, these TDA 214, actually, most of these 70 amp smart power stages are really good in terms of their efficiency, but the TDA 21472s are a bit better than most. And then going up, actually, wait, no, I misread my notes. That's only 250 watts, 250A, and still 20 watts. But yeah, that's still a really great efficiency right there. Going up further to 300 amps output, you're going to be looking at about 25 watts of heat dissipation, which, again, like, I mean, I don't need to tell, like, the efficiency is just up there. And I'm really sad that they didn't go for a 14 phase. Like, seriously, it would have been insane how efficient this VRM would have ended up being. But anyway, going from 300 amps to 400 amps. So I think ultimately, like, stock, the card runs in that 200 to 250 amp range. 300 amps up, you're going to be looking at overclocking, and the higher the current, you're going to be, looking at like extreme cooling methods to hit the higher currents, if the card even scales to that kind of current level anyway. But 400 amps, you're going to be looking at about only 40 watts of heat. And 500 amps, you're going to be looking at about 60 watts of heat. So at this point, the VRM starts actually, like, we get a pretty major increase in heat dissipation going from 400 amps to 500 amps. And then 600, actually my notes don't have 600 amps, which is also, like, unfortunately the data sheet ends at 60 amps anyway. So we couldn't really go past that. And I doubt anybody's going to run these on LN2 anyway. So yeah. And if they do, I'm not sure if they'll even scale to 500 amps, right? We still, we still have to see about that. But still, for normal usage, this VRM is really, really efficient. So that's great. For extreme overclocking, who knows? Like, it really depends if the card even needs that much current when on LN2. And I don't know that we'll find out, because I'm not buying one of these. I don't plan to. And it's not competitive with a 2080 Ti, so I really doubt anybody's going to seriously bench one of these. So yeah, that kind of sucks, because this is a really nice VRM, and it would be even nicer if it had all 14 phases. But anyway, moving on to the other main VRMs. We're not going to talk about the other, like, circled regulators, because quite frankly, I don't know which one of them is which. And there's a bunch of them that have to be on the card. So we have like 1.8 volts for the HBM. There's going to be a PEX rail. There's a PCIe rail. There's a display drive rail. PCIe, which usually those two are combined. So PCIe and display. Yeah. Oh yeah, there's also the 5 volts rail, and unfortunately there's like more regulators on this card than I know like common AMD voltage rails for. So evidently AMD has added a couple new ones, but I don't know what they are. So anyway, moving on to the ones that I do know what they are, we have down here HBM power, which is a 2-phase. So that's our HBM VRM right there, 1 and 2. And then down here we have VDDCI, and VDDCI is normally on like AMD's GDDR5 based cards is normally huge. Okay, like if you look at like 7970s or 7950s, there are multiple 7970s and 7950s with like 2-phase VDDCI because the VDDCI rail used to be so power hungry, and that's the memory controller. In fact, VDDCI used to normally pulled more current than the memory itself did. So yeah, that's kind of an interesting like difference between the older cards and the HBM cards, where now the VDDCI rail is this cute little adorable thing right here, which is a single phase, and that is a IR35401 power stage, and that's a 20 amp part. So like this thing, you know, this is a really low current rail, where previously this thing would like on a 7970, this would straight up blow up. Because if I remember correctly, 7970s at stock average like 15 amps on that rail. So yeah, interesting how the HBM memory controller needs so much less power. Now that the card has 4 HBM chips, the HBM VRM itself has gotten quite an upgrade, right? So the HBM VRM is on the TDA 21472s, and that's going to be controlled by this chip right here, which is another 35217. And then we get this VRM over here, which is the SoC regulator. So yeah, Vega has a system on a chip portion. And that's another 2-phase, and that's also hanging off of this 35217 down here. The VDDCI, I'm assuming, is running off of the 35217 on the back, because this one is obviously, like, that one's maxed out at 7+1, right? And so this one straight up couldn't run it can't do a 7+2, right? Which you need that +2 for the HBM and the Soc Rails. So this 35217 here is running in 2+2 configuration for HBM and SoC. Both of those are again on more TDA 21472s, which is probably ridiculous overkill for both of them, because the HBM generally doesn't pull that much power. I mean, the HBM power on a Vega 64 was like, a Vega 64 has 2 HBM stacks, or HBM2 stacks, and that one, like, quite frankly, that VRM was a single phase, and it wasn't good enough for more than maybe, if I remember correctly, it was good for like 30 amps max or something. So the new HBM VRM is actually kind of overkill, and kind of an odd decision in my opinion. I do wonder why AMD didn't opt for like a weaker HBM VRM and then, you know, spend more money on the V-Core. Like, I'd prefer that, but anyway, here they decided that, you know, they're going to go for a really, really powerful HBM VRM. I guess it might be for the 32 gig variant of the card. Because logically, the 32 gig HBM, it has more, like, there's more memory chips in those stacks, so they would pull more power. So I guess that's why we have the 2-phase HBM now. Whereas previously it was like an anemic single phase. So that's an interesting difference. But and finally we have the SoC rail, which is the same as the HBM. So yeah, that there is the Radeon VII reference PCB. It's it is actually more efficient than a reference Vega 64. Like, even though it has less phases, the individual phases are much better than what you got on a Radeon Vega, like on the Vega 64s, just because the TDA 2147s are absolutely stupid in terms of their efficiency. Like, these are awesome and super expensive as a side effect. But this is ultimately, like, even though it's a 10 phase, it's actually more efficient than the 12 phase you got on a Vega 64. Also, because I think thermally this VRM works out to be less dense, it should actually be less hard to cool without a heatsink. So that's kind of fun. And then for HBM, we've gotten a huge upgrade on the HBM VRM. VDDCI's got a bit of an upgrade as well. Previously, it was just a minor, like, it was basically that. That used to be VDDCI on like a Vega. And then SoC had like, well, I don't remember Vega. I'm not sure Vega had an SoC rail. I don't think it did. So that one's new. And I'm not sure how much current it needs. So that's kind of that. Yeah, that's the Radeon VII. Like, it is very complicated, right? And the layout's rather unique. And overall, I'm a fan of it. But then again, it's like, when have I not been a fan of an AMD reference design? So, yeah, that's it. So thanks for watching. Like, share, subscribe, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support Gamers Nexus, there's store.gamersnexus.net where you can pick up things like the mod mat you can see in the background, shirts, I think glasses, mugs, and that kind of thing. And there's also the Gamers Nexus Patreon. And also, if you'd like to check out more content from me, there's I have a channel called Actually Hardcore Overclocking where I do more PCB breakdowns and other overclocking related content. So yeah, if you'd like to check that out, that would be cool. Thanks for watching, and goodbye.